Welcome to the Physiological Fluid Mechanics course. In this presentation, I will be introducing the fundamentals of fluid flow in microfluidic devices and focus on the use of surface tension in device design. I'll start with a basic demonstration of capillary effect and then define microfluidic flow. I will further use scaling laws to evaluate the effect of significant forces and finally discuss how surface tension is useful in the context of microflow. In this demonstration from the 101 kids experiments, we take a piece of tissue and place one end of it in the glass full of water and the other end is placed in an empty cup. Over an extremely long period of time, we observe that the tissue paper becomes saturated and transports water into the empty cup. This transport continues until the level of fluid becomes equal on both ends. This happens due to rise of fluid through the micropores in the tissue, a phenomenon called capillary rise. So what is microfluidics? We often hear the terms lab on a chip and microelectromechanical systems called MEMS, which are essentially talking about instruments which are small. Microcomputing systems used in computers are analogous to microfluidic devices. Just like parallel processors have become everyday use objects, microfluidic devices are transitioning from being novel, specialty use devices to everyday use technologies. The important point to note while defining microfluidic devices is that the size of the instrument is not necessarily in the microscale. However, the volume of fluid that is processed in these systems are usually in microscopic quantity, sometimes down to the order of 10 power minus 21 liters. One of the simplest examples of microfluid flow in nature is the transport of nutrients in trees from the soil to the roots to the leaves, which are at the tallest point. The air on the surface of the leaves evaporate water and create a pull in the water columns of the trees, which propagate to transport the water at the roots to the leaves at the top of the tree. The water at the roots enter the tree's capillaries through osmosis, a selective transport of solvent from low solute concentration side to high solute concentration area. It is amazing to note that all of this occurs passively without the use of active energy systems like pumps. So what are some of the advantages of the microfluidic devices? Importantly, the ability to manipulate small volumes of fluid, sometimes in the order of molecules. The other advantages are low consumption of reagents, quick system response, higher efficiency due to minimal use of energy. Most of these devices are portable and user-friendly. They are less prone to human error, making it repeatable, and it is an excellent way to study biological systems. At microscopic level, the physics which govern the flow of fluids is significantly different from that of macroscopic flows. Atomic forces, intermolecular forces, and thermal fluctuations of atoms are still negligible as they are significantly smaller in scale compared to the microchannel flow of the order 1 micrometer. However, surface tension, magnetic forces, and electrical forces, which are insignificant in macro systems, become significant in microsystems. So let's now compare the effect of surface forces like viscous forces to volume forces like gravity in the context of microflow using scaling. Pause to ponder how they scale. So surface forces scale as length squared, while volume forces scale as length cubed. This makes the ratio inversely dependent on the length. We can see that as length becomes small, the ratio tends towards infinity, suggesting that at extremely small length scales, the volumetric forces are insignificant. You can similarly compare electrical forces to gravity as an exercise. What about pressure-driven flows? We can use Hagen-Poiseuille's equation to estimate the pressure drop of a microchannel over a length of 1 centimeter for a flow rate of 1 milliliter per second. Pause and ponder what the magnitude of pressure drop is compared to atmospheric pressure. So if we assume the fluid to be water and then move all the terms to the other side to find delta P, we get this expression. So let's go step by step. So we have the 8 from here. For Q, we are substituting 1 milliliter per second and then converting the units from milliliter per second to meter cube per second. And then we have the length in centimeters, convert that into meters, and then use the viscosity as it is. And we are given the diameter, and the radius is half of it, and to the power 4. So when you solve for this, you get this giant expression. How does that compare to atmospheric pressure? So the ratio of the delta P required to drive the flow with that of the atmospheric pressure is almost 36 times the atmospheric pressure. And this is a ridiculous number. And hence, pressure-driven flows are impractical in microfluidic systems, and surface tension, capillary rise, and electrostatic forces are the more viable options. This brings us to the topic of surface tension. We are all familiar with the concept, and hence I'm going to quickly summarize the fundamentals. I suggest referring to Nanofluidics and Microfluidics by SP and Yom as recommended reading. A molecule in the bulk liquid experiences cohesive forces with other molecules in all directions, leading to a net zero force. A molecule at the surface, however, experiences only a net inward cohesive force. The difference in the cohesive energy over a surface area is represented by surface tension. If you pause to ponder what the units are, you'll realize that since it's energy over area, the units are joules per meter square, or simply Newton per meter, suggesting the behavior of surface tension as a force. If a tube with a small diameter is immersed in water, we notice a rise in the water level of the tube above the free surface. This is called capillary rise. At the interface of the water and the glass tube, there are molecular interactions between the unlike particles causing attractions. This is called adhesion. The adhesive forces pull the water up at the interface. As I previously mentioned, there are cohesive forces between the like particles of water causing it to act like a membrane. This pulls the water, forming a meniscus. The angle of meniscus is called contact angle. Contact angle is different for different fluids, and it also depends on the solid material in contact, while the surface tension is dependent on the fluid alone. The forces acting on the fluid interface are due to atmospheric pressure and surface tension. The expression for capillary rise can be derived by balancing the weight of the liquid, pi r square h rho g, and the upward force due to surface tension, 2 pi sigma cos theta. The capillary rise is given by this expression called Jurin's law, and it shows that capillary rise is inversely proportional to the radius of the tube. The next important question is, what is the timescale over which this happens? We've seen that the tissue paper took forever to transport the fluid across in the macro scale. The timescale is simply given by capillary rise squared over something called a simplified diffusion coefficient. If you look closely, you'll realize that the expression is similar to the timescale of diffusion with an additional dependence on surface tension. Lucas Washburn derived an expression linking capillary height, time, surface tension, and contact angle. So let's clean this expression up to get the T capillary on the left-hand side, and we get this expression. As we can see that the h square is right here, while the diffusion coefficient has both the surface tension and the fluid viscosity in its term. Let's now talk about the home use pregnancy kit, which works on the principle of capillary rise. So the device has an absorbent pad which acts as a capillary. You put the liquid analyte on one end and the liquid rises through the capillary. If the analyte has the specific biomarker, they interact with the particles in the capillary and give out a visual indication confirming the presence. Instead of a single column, the material is a bundle of capillaries idealized as a porous material. Let's now put some numbers into test. Current microfluidic systems employ capillary tubes of approximately 100 micrometers in diameter. Suppose we use water as the analyte and a tube contact angle of 60 degrees. Pause to solve for capillary rise using Jurin's law. Hope you had a chance to solve the equation. So if we substitute the numbers, we have the surface tension given, we have the cos theta given. We are assuming it's water, so the density will be 10 power 3 kilogram per meter cube, and acceleration due to gravity will be 10 meter per second square, and the radius will be half of the diameter. So when we solve this, we get the height to be 0.144 meters, which is 14 centimeters. And when you compare it to the scale of the device, it is an extremely large rise. Similarly, if you try to use the Washburn's equation to estimate the time for the capillary rise, you can use this expression, and when we substitute the numbers in for the viscosity, the capillary height from the previous equation, the surface tension of water, the radius, and the contact angle, we get the time to be about 20 seconds, which is tremendously fast response time for a home use kit. The other important transport mechanisms that aren't discussed in this lecture but are important in microfluidic device design are diffusion, osmosis, thermal expansion, flow due to electrical charges, and flow due to magnetic charges. You can learn more about these transport phenomena by reading the book Transport Phenomena in Microfluidic Systems by Panigrahi. So to summarize, we have seen how capillary rise can be used to transport liquid. It takes an extremely long time over macro scales, but it still occurs without the use of active energy. We then defined microfluidic flow and talked about the various advantages of it. We use scaling laws to show that forces acting on surface dominate volumetric forces at microscales. And lastly, we discussed how capillary rise could be used as a great transport mechanism in microfluidic devices. Hope you learned something valuable through this presentation. My name is Vinil, and thank you for watching this video.